Right, so picking up where we left off with non-homogeneous equations, in our last lecture we talked about how to find a guess based on the inhomogeneous term, and this guess we could eventually develop into a particular solution so that we could find the general solution to the whole ODE. There is a situation in which that guess will not work. It's called duplication. Duplication is a phenomenon in which the guess is part of the complementary solution. Now, at first, that might not sound so bad. So let's just look at an example of what happens if that occurs. So let's say we're trying to find the general solution of y prime prime minus 4y prime plus 4y equals e to the 2x. Okay, well, definitely we're going to need the complementary family and a particular solution. So let's start with trying to find the complementary family. So we need to look at the associated homogeneous equation, which in this case is y prime prime minus 4y prime plus 4y equals 0. Now, you can use the characteristic equation. That looks like r squared minus 4r plus 4 equals 0. And then that factors into r minus 2 squared equals 0. So we have exactly one root with a multiplicity of 2. That gives rise to the solution y1 equals e to the 2x. And also, since we have a multiplicity of 2, we can get the other solution by saying y2 equals x e to the 2x. Okay. So now the complementary family is going to be all the linear combinations of these. c1 e to the 2x plus c2 x e to the 2x. Right then. So let's look at the guess that we would make in order to find the particular solution, because that's the other part we need, right? The guess that we would make based on the inhomogeneous term alone is a e to the 2x. Now there is a problem here. There is a problem here because a e to the 2x is part of this family of functions. You can set a and c2 and c1 such that they are the same. That's a problem because that means that if you plug this function into the left-hand side, which we normally do in order to figure out what a is, we'll just get 0. Don't take my word for it. Let's actually do it. So yt prime is going to be 2a e to the 2x, and yt prime prime is going to be 4a e to the 2x. You put that into this ODE right here, you get 4a e to the 2x minus 4 times 2a e to the 2x plus 4 times a e to the 2x. This should be equal to e to the 2x. All right. Well, let's see here. We have 4 minus 8 plus 4. I'm pretty sure that's just 0a e to the 2x. Now, e to the 2x is never 0, so I guess that means that 0a equals 1. So in other words, a is 1 divided by 0. See the problem? Okay. So what this means is that if you have your guess being part of the complementary family, you're going to have to do something different. Your guess will not work as it is. This phenomenon, like I said, is called duplication, when the guess is part of the complementary family. Okay? So, how do we deal with this? Well, the procedure is very simple. You just get rid of your guess, and you come up with a new guess. And the new guess is just going to be the old guess multiplied by x. So ax e to the 2x. And then you check once again whether duplication is occurring. In this case, the answer is yes. You still have duplication because ax e to the 2x, as long as you set c1 to be 0 and c2 to be a, these will be the same thing. So we still have duplication occurring, so we have to do that same procedure again. We throw out the guess and come up with a new guess. The new guess is going to be the previous guess multiplied by x. So ax squared e to the 2x. And now you once again check for duplication. This is no longer duplication because no matter what you set a to and c1 and c2 to, these functions will be linearly independent. Great. So now the guess will work. Okay? And then we proceed from here to find a. So let's go ahead and do that. By the way, the whole multiply by x thing to make the new guess, that sounds really simple, right? But sometimes it can make the derivative much more complicated. Like in this case. So yt prime, we're going to have to do the product rule. So the first times the derivative of the second plus the second times the derivative of the first. So let's see here. Altogether, this comes out to be 2a times x squared plus x e to the 2x. And then you take the derivative again. We're going to need two derivatives because we're going to want to plug it into this second order ODE. This is going to be, okay, first of all, we need the product rule once again. So the first times the derivative of the second plus the second times the derivative of the first. Like that. This turns into 2a times something times e to the 2x. The something is going to be, let's see here, 2x squared plus 2x makes plus 4x. And then plus 1. So we have this as our second derivative. Okay, so we're going to plug that into this ODE. So we'll get 2a times 2x squared plus 4x plus 1 times e to the 2x. Subtract from this 4 times 2a times x squared plus x e to the 2x. Add to this 4 times the original, which is ax squared e to the 2x. All of this together should be equal to e to the 2x. Okay, so there's quite a lot of like terms to combine. I'm going to erase this part because as of right now, this is all we'll need. So I'm going to erase this part. So first of all, we can distribute some stuff. We can say 4ax squared plus 8ax plus 2a multiplied by e to the 2x. Add to this negative 8a x squared minus 8ax e to the 2x. Add to this 4ax squared e to the 2x. And all of this together should be e to the 2x. Okay, so let's see here. 4ax squared minus 8ax squared plus 4ax squared is just going to be 0ax squared. Then we have 8ax minus 8ax, that's also 0. Then we have 2a, and nothing cancels with 2a, so 2a times e to the 2x equals e to the 2x. Well, that makes it pretty clear that 2a has to be 1, and therefore a has to be 1/2. So, what that means is that the particular solution, or a particular solution of this ODE, would be 1/2 x squared e to the 2x. Right? Because our initial guess was ax squared e to the 2x. Well, that wasn't the initial guess, but that was the refined guess, I should say. Okay? And so now, as in the previous lecture, to find the general solution, you just add together the complementary family and the particular solution. So we have this. And that's our answer. Okay. So very much the same stuff as we did in the previous lecture, just with the added step of maybe you have to refine your guess a little by multiplying by x some number of times. Okay? So of course, we're going to do some more examples. Let's suppose we have an initial value problem. This one is y prime prime plus 9y equals cosine of 3x plus sine of 3x with the initial conditions y of 0 equals 2 and y prime of 0 equals 1. Okay, so this all together is our initial value problem. Okay, so first thing we ought to do is find the complementary family, which we do by first writing down the associated homogeneous equation. The associated homogeneous equation is just going to be y prime prime plus 9y equals 0. Right? right? Because we're just setting everything that doesn't have y or a derivative of y attached to it equal to 0. This gives us the characteristic equation r squared plus 9 equals 0. And that gives us that r is plus or minus 3i. Okay, so as always, we look at Euler's formula. E to the 3ix is going to be cosine of 3x plus I times the sine of 3x. And then in that case, our complementary family is c1 cosine of 3x plus c2 sine of 3x. All right, so now here's the part where we try to develop a guess. Based on what we have here, the initial guess ought to be a cosine 3x plus b sine 3x. So let's write that down. Yt equals a cosine of 3x plus b sine of 3x. However, as you can see, there's duplication happening because if you just set A to be C1 and B to be C2, then these are the exact same thing, right? So we need to forget about this guess and come up with a new guess. The new guess we create by multiplying the previous guess by x. That's always how we refine the guess. We just multiply it by x. Okay. So x times a cosine of 3x plus b sine of 3x. Okay, and now duplication no longer occurs because now x cosine of 3x and x sine of 3x, those are both linearly independent from this thing. So now we can proceed. We're going to need two derivatives of this thing. Let's do it over here. The first derivative, we're going to have to use the product rule, so that's going to be the first times the derivative of the second. Plus the second times the derivative of the first. Okay. And then to make our lives a little bit easier, we can simplify this, I think. When I say make our lives easier, I mean make the second derivative easier. Let's see here. We have 3bx plus a times cosine of 3x plus negative 3ax plus b sine of 3x. All right, so then for the second derivative, yt prime prime, let's see, we're going to have to do the product rule on both terms here. So we're going to have 3bx plus a times negative 3 sine 3x. Add to this 3b cosine of 3x. Then add to that negative 3ax plus b times 3 cosine of 3x minus 3a sine of 3x. Okay, and once again, because we're going to use this later, let's try to combine some like terms so that we can, you know, make it easier to work with. Let's see here. We have something times cosine of 3x plus something times sine of 3x. Okay, let's see. The something multiplying by cosine of 3x is 3b plus another 3b minus 9ax. So that's 6b minus 9ax. Then the thing multiplying by sine is going to be negative 3a minus 3a, so that makes negative 6a, minus 9bx. Okay. It's a mess, but that's what we're dealing with, right? So, we put this information into the original ODE. We get here, let's see here, negative 9ax plus 6b cosine of 3x plus negative 9bx minus 6a sine of 3x. That's the second derivative. Then add to that 9 times the original. So add to that 9ax cosine of 3x plus 9bx sine of 3x. And all of this together should be cosine of 3x plus sine of 3x. Okay, so let's see here. Negative 9ax and 9ax cancel, so we get 6b cosine of 3x. And then over here, negative 9bx and 9bx cancel, so we get negative 6a sine 3x. Is equal to cosine of 3x plus sine of 3x. Okay. Now, cosine 3x and sine 3x are linearly independent functions, so therefore the coefficient on cosine 3x here is equal to the coefficient on cosine 3x here, which means 6b equals 1. And on the other hand, negative 6a is also going to be 1 because it's the coefficient on sine 3x. So negative 6a equals 1. And what we get here is b equals 1/6, a equals negative 1/6. Okay. So, to put it all together, the particular solution is going to be x times negative 1/6 cosine of 3x plus 1/6 sine of 3x. And then the general solution is just the sum of that and the complementary family. So the general solution is just going to be y equals c1 cosine of 3x plus c2 sine of 3x plus, well, we can distribute that x to make it into minus 1/6 x cosine of 3x plus 1/6 of x sine of 3x. That's the general solution. Okay. Now we're not done. We're not done, right? Because we have an initial value problem. So I'm going to erase this now. And we're going to use the initial conditions to figure out the particular solution that solves the initial value problem. Okay, well, first of all, I suppose we can combine some like terms here. We can say this is c1 minus 1/6 x cosine of 3x plus c2 plus 1/6 x sine of 3x. This is y. It's y. So we're going to need a derivative of that. So y prime, okay, two product rules. So first times derivative of the second plus the second times the derivative of the first. And then the same thing over here. First times derivative of the second plus the second times the derivative of the first. Okay, so let's put this stuff together. We have here 3c2 minus 1/6 plus 1/2 of x times the cosine of 3x. Add to this, let's see here, negative 3c1 plus 1/6 plus 1/2 of x times the sine of 3x. Okay. So the initial conditions imply that 2 has to be y of 0. Y of 0 is going to be, let's see here, c1 minus 0. Cosine of 0 is 1. And then the sine of 0 is 0, so we can just forget about that term. Meanwhile, 1 has to be y prime of 0. So that's going to be 3c2 minus 1/6 plus 0 times cosine of 0 is 1, and then sine of 0 is 0. All right. Well, that makes it pretty clear, first of all, that c1 is 2. Next up, 3c2 minus 1/6 is 1, so therefore 3c2 is equal to 1 plus 1/6. And then that means that c2 has to be 7/18. looks like I made a mistake in my notes. Well, that's fine. I can fix that later. So, the particular solution that solves our initial value problem is going to be, let's see here, 2 cosine of 3x plus 7 over 18 sine of 3x minus 1/6 x cosine of 3x plus 1/6 x sine of 3x. And that's our answer. It's quite a lot, isn't it? Just multiplying by x one time made this much more complicated, I think, just because that's how the product rule works. All right. So let's do another example. This one is going to be another initial value problem. It's a fourth order ODE. This just equals 5. Y of 0 and y prime of 0 and y prime prime of 0 and y prime 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 of 0 are all going to be 0. Okay, so first thing we have to do is find the associated homogeneous equation, which looks like fourth derivative of y minus y equals 0. Then that gives us the characteristic equation r to the fourth minus 1 equals 0. R to the fourth minus 1 can be factored into r squared minus 1 times r squared plus 1. R squared minus 1 can be factored into r minus 1, r plus 1. And then r squared plus 1 is irreducible. So what we get here are 4 distinct roots. One of them is 1, another is negative 1, a third is I, and a fourth is negative I. So, first of all, we get the solution y1 equals e to the x, and then y2 equals e to the negative x. And then as for I, well, if you look at e to the ix, that is cosine of x plus I times the sine of x. Therefore, y3 is cosine x, and y4 is sine x. So, the complementary family is going to be e to the c1 e to the x plus c2 e to the negative x plus c3 cosine of x plus c4 sine of x. Okay, next up we're going to have to create a guess. So, this is a 0-degree polynomial. Therefore, our guess is also going to be a 0-degree polynomial. We have to check for duplication. So, is any part of this a 0-degree polynomial? Well, no. No part of this is constant. So no duplication is occurring. Great. Then we take a few derivatives of this thing. Yt prime is going to be 0. Yt prime prime, as well as yt third derivative, as well as yt fourth derivative are all going to be 0. So what we're looking at here is 0 minus a equals 5. That makes it pretty clear that a is negative 5. Okay, so then in that case, the particular solution is just going to be negative 5. From here, you add the complementary family and the particular solution to find the general solution, which is c1 e to the x plus c2 e to the negative x plus c3 cosine x plus c4 sine x minus 5. And that's our general solution. So now to find the particular solution that solves the initial value problem, we need to use all of these initial conditions. So first of all, we're going to need 3 derivatives of this thing. So the first derivative is c1 e to the x minus c2 e to the negative x minus c3 sine x plus c4 cosine x. And the derivative of negative 5 is just 0. Second derivative is c1 e to the x plus c2 e to the negative x minus c3 cosine x minus c4 sine x. The third derivative is c1 e to the x minus c2 e to the negative x plus c3 sine x minus c4 cosine x. Okay. So then we can use the initial conditions to set up a system of equations for this. I'm going to erase this part because we no longer need it. And in fact, I'm going to erase this as well. And I'm just going to say that the general solution is going to be c1 e to the x plus c2 e to the negative x plus c3 cosine x plus c4 sine x minus 5. So 0 has to be y of 0. Y of 0 is apparently going to be c1 plus c2 plus c3, cosine of 0 is 1. c4, sine of 0 is 0. And then minus 5. Then we have 0 equals y prime of 0, which is going to be c1 minus c2 minus C3 sine of 0 is 0, plus C4. Then 0 needs to be y prime prime of 0, which is going to be C1 plus C2 minus C3 and 0 has to be the third derivative of 0. So that's going to be C1 minus C2 minus C4. Okay, so then this is a system of equations that we can solve for C1, C2, C3, and C4. So let's see here. I suppose the way that I would choose to do this is, first of all, I would add the second and fourth equations. If you do that, then you'll get 0 equals 2c1 minus 2c2, and then the c4s cancel. Then I'd add the first and third equations. If you do that, you'll get 5 equals 2c1 plus 2c2. I moved the 5 over to the left-hand side in case that wasn't clear. Now you can add these two equations. If you add these two equations, you'll get 5 equals 4c1, which means c1 is 5 over 4. C1 is 5 over 4. Meanwhile, C1 minus C2 is 0. So therefore, C2 is also 5 over 4. Okay. In that case, the first equation becomes 5 equals 5 over 4 plus 5 over 4 plus C3, which is just 5 equals 5 halves of plus C3, and therefore C3 equals 5 halves. The fourth equation turns into 0 equals 5 fourths minus 5 fourths minus C4, which means C4 is 0. And so what we get out of this is the slightly chaotic solution. 5 fourths e to the x plus 5 fourths e to the negative x plus 5 halves cosine of x minus 5. Minus 5. So that one had no duplication. Its main challenge was the fact that it was an initial value problem, right? Which normally means that it's just one more step. You just have to put in the initial conditions. But as you can see, in this case, you get a whole system of equations that you need to solve. Let's do another example. This will be the last one for today. Let's suppose we're trying to find the general solution of third derivative of y plus second derivative of y equals 3e to the x plus 4x squared. Right, so once again, the associated homogeneous equation is the first thing we ought to look at. By the way, some of you might be wondering, should we find the complementary family first or find the particular solution first? My answer to that is that you need to find the complementary family first because that tells you whether you have duplication or not. So this turns into the characteristic equation r cubed plus r squared equals 0. We get from this r squared times r plus 1 equals 0. Therefore, we have two roots here, r1, which is 0, which has a multiplicity of 2, and r2 is negative 1, which has a multiplicity of 1. That implies the existence of two solutions for 0. We have y1 is e to the 0, which is 1, and then x times that, which is just x. And meanwhile, we have r2 coming in with y3 equals e to the negative 1x. Okay, so then our complementary family is going to be c1 plus c2x plus c3e to the negative x. All right. Now let's talk about the particular solution, because we're going to have to come up with a guess, right? Based on the inhomogeneous term here, the guess should be a e to the x plus, okay, we have a second degree polynomial, so our guess should also be a second degree polynomial. Therefore, it should look like bx squared plus cx plus d. But you look at this for a second and you realize you've got duplication. You've got duplication because if you set a and b to be 0 and c3 to be 0, then these are basically the same function. So we're going to have to alter our guess. We're going to have to throw this out and come up with a new guess. The way that you come up with a new guess is you take the previous guess and you multiply a factor of x by whatever part is causing trouble. In this case, the a e to the x is not the problem. So don't multiply x by that. Instead, just multiply x by the polynomial part. So a e to the x plus bx squared plus cx plus d times x. Which, by the way, is the same thing as a e to the x plus bx cubed plus cx squared plus dx. We've still got duplication, because if you set a, b, and c to be 0, you get dx, which is part of the complementary solution. So once again, you cross it out, and you multiply another factor of x by the polynomial part. So ae to the x plus bx squared plus cx plus d times x squared. That turns into ae to the x plus bx to the fourth plus cx cubed plus dx squared. And then finally, this is completely linearly independent from this. So we have no more duplication to worry about. Now then, we're going to need to take this and plug it into the original ODE. So we'll need two derivatives, or actually three derivatives. Good news is these derivatives are actually fairly easy. ae to the x plus 4b x cubed plus 3cx squared plus 2 dx. Second derivative is going to be ae to the x plus 12b x squared plus 6cx plus 2d. Third derivative is going to be ae to the x plus 24b x plus 6c. And then the derivative of 2d is just 0. So we're supposed to add the second and third derivatives and get that on the right side. So let's see here. We should have ae to the x plus 24bx plus 6c. Add to this ae to the x plus 12bx squared plus 6cx plus 2d. This should equal 3e to the x plus 4x squared. All right, so we have some like terms we can combine. We'll get 2ae to the x plus 12bx squared plus 24b plus 6c times x plus 6c plus 2d equals 3e to the x plus 4x squared. So now e to the x, x squared, x, and x to the 0 are all linearly independent functions. Therefore, the coefficients on the left are equal to the coefficients on the right. Therefore, we get a system of equations that looks like 2a equals 3, 12b equals 4, 24b plus 6c equals 0, and 6c plus 2d equals 0. So that makes it pretty clear that first of all, a is 3/2, that b is 1/3. Therefore, this third equation turns into 1/3 of 24 is 8, plus 6c equals 0. Therefore, 6c equals 8. Therefore, c equals 4/3. And if c is 4/3, then 6 times 4/3 would be 8. So 8 plus 2d equals 0. That makes it pretty clear that D is -4. So the particular solution that we're looking for, yp, that's going to be, let's see here, 3/2 of e to the x plus 1/3 x squared, x to the 4th, plus 4/3 x cubed minus 4x squared. And then in that case, our general solution is just the sum of the complementary family and the particular solution. So the general solution is just going to be y equals c1 plus c2x plus c3 e to the -x plus 3/2 e to the x plus 1/3 x to the 4th plus 4/3 x to the 3rd minus 4x squared. And that is that. Okay. So, moral of the story, non-homogeneous equations are difficult, in case that wasn't already clear. In any case, that's all for today. See you in the next one.